Ladies and gentlemen, may I have your attention, please? We'll be starting in a few minutes. As a warm reminder, please switch your mobile phone and other electronic sound-emitting devices into vibration mode. Please note that in this seminar, there'll be a Q&A and panel discussion section for you to raise questions and exchange with our speakers. You may raise your hand if you have any questions, and our staff will pass you a microphone. For our online forum participants, you may submit your questions through the Q&A function on the HKLF mobile app. Thank you for your attention. Good morning, our Honorable Laureate, distinguished scientists, ladies and gentlemen. Welcome to the science seminar of Star's Journey in our Milky Way Galaxy, organized by the Council of the Hong Kong Laureate Forum, namely the HKLF, together with the Hong Kong Space Museum. First of all, allow me to introduce myself. My name is Tasha, and it's my absolute honor to be your Master of Ceremony today. On behalf of the co-organizers, we'd like to welcome everybody joining us in person today, and we'd also like to extend our heartiest welcome to our online participants joining us through the live webinar today. So thank you so much. Now, to briefly introduce, we have an excellent program and a great lineup of speakers today, and we're much honored to be joined by three scientists in astronomy who'll be sharing with us their study and knowledge. The Shaw Laureate in Astronomy in 2022, Professor Michael Perryman. Welcome, Professor Perryman. And two promising scientists from Hong Kong, Professor Chu Ming Chung and also Professor Quentin Parker. Let's welcome our scientists with a big round of applause. Thank you so much for joining us today. Now, to officially kickstart today's program, may we now invite our moderator of today's seminar, Professor Quentin Parker, Professor of Faculty of Science and Director of Laboratory for Space Research at the University of Hong Kong, to come on stage to deliver the opening remarks and also to introduce the first speaker for us. Professor Parker, please.
Thank you very much indeed. Well, it's a great honor and privilege actually to be standing here. I'm sorry for the croaky voice. I caught a very bad cold a few days ago, but like all good astronomers, we just carry on and push through whatever things are put in front of us. So it gives me a really great honor to be here today and to introduce two fantastic speakers have tremendous track records of achievement in the field. Myself, I'm, as I said, Director of the Laboratory for Space Research at the University of Hong Kong. I'm an Australian. I came from Sydney before I came here about 8 years ago, and tremendous that I am to be at the University of Hong Kong. I'm also vice chairman of a company called OASA. It's an NGO, but it stands for Orion, the Hunter, the Constellation, Astropreneur, Space Academy, And it's all about the new space economy and about trying to get young kids, such as so many I see here today, into STEM education, which I think is really important. I'm sure all the speakers will agree. So I want to say a few words about Professor Perryman. He is not just a Shaw Laureate from 2022 and an adjunct professor at Dublin, but probably one of the great leaders of astronomy in the field of what is parallax measurements and getting distances to stars. I mean, we all know about parallax. If you close one eye and then the other and look at something in the background, things move backwards and forwards. The same basic trigonometric technique is used now in space. First with the Hipparcos satellite, he also led. Then after that, the tremendous Gaia satellite, which he's basically also led until its launch. And this has been transforming our understanding of our galaxy by getting distances to, I thought it was just over 1 billion, but I've now been updated with the latest information from Professor Perryman himself. About 3 billion stars will have their distances measured to very high accuracy through this incredible astrometric satellite. So the kind of science that he will show in his presentation, I had the privilege of having a look at the presentation before it's giving it, and I must say I went through it a few times. The videos are astonishing. I'm sure people are going to be blown away by your presentation, Professor Perryman. And so, you know, if you look at, you can find Professor Perryman easily online. You can do a Google or a Wikipedia, and you'll find out the accolades and the achievements and the tremendous track record of this fantastic scientist. I'm sure his ears are sort of burning with. Anyway, I'm not exaggerating in all of these things I'm saying. And so I've had 5 minutes to give this brief introduction to the first speaker. The second speaker, Professor Chu, I'll say a few words later on his great achievements as well. But for now, I'd like to finish and invite Professor Perryman to come up and give his presentation. Thank you very much.
Well, good morning, everybody, and it really is a great pleasure to be here and to welcome you here. Thank you very much, Professor Parker, for your very kind words of introduction. My talk comes at the end of what has been a wonderful week, for those of you who haven't participated, the Hong Kong Laureate Forum, where we have been treated with a week of fantastic visits to laboratories, to schools, to universities. We've been treated with the most remarkable hospitality, and I would like to thank everyone for what has been a fantastic week. Now, my task today is to talk a little bit about my research, or the research that's ongoing and that I've been awarded this wonderful Shaw Prize for. It's a mixed audience. It's not a specialist audience of astronomers, so I'm going to try and target my talk to be accessible to everybody. The great problem, I think towards the end of our careers, we enormously enjoy giving talks to the public, to the non-specialists, to try and explain what it is we've been doing, what it is we've been funded to do. At the same time, it's a great challenge to talk to a wider audience, because by definition, we are at the cutting edge of science, which means that the concepts that we deal with every day are very difficult, very challenging, even for people in our own field. If I try and explain the details of Gaia to people who are well-versed in astronomy or even well-versed in space techniques, the number of complexities or the challenges and so on is difficult even for experts to understand. So what I hope you will get out of this today is a general picture of what it is we've been doing and perhaps why it's important. Now, is it worth lowering the lights just a little, because your attention will be on the screen and not on? So from time immemorial, of course, people have looked up at the night sky in wonder and in mystery and tried to understand what the stars are. And it may surprise you to know that it was less than 100 years ago that we first understood the energy mechanisms of the stars. This is nuclear burning, mainly the fusion of hydrogen into helium, But it was only around 1927 that these first ideas really formed a consistent theory. And of course, ever since the time of the ancient Greeks, or before, the ancient Chinese astronomers amongst them would look at the stars and try and figure out what they told us. What does it mean? What are they saying? And to the ancient Greeks of the Hellenistic period in particular, they were puzzled that the heavens appear night after night exactly the same, the stars relative to each other. Of course, there's motion of the stars, but in fact that motion we understand clearly today due to the rotation of the Earth and not of the sky. And in this little animation you can see a rather non-conventional view of the heavens where we fix the sky and the Earth is rotating. And the relative positions of these stars seems to say the same. And what mystified the Greek astronomers, that there were a number of objects which moved in the sky that didn't stay the same. These were the sun, of course, the moon, of course, and the 5 or 6 planets that were known at the time. Planet, the word planet in English comes from the ancient Greek planete, which is wanderer. They were called the wanderers. And the ancient Greeks had no idea what these planets were. They just knew that they moved in a mysterious way. And it took perhaps another 2,000 years before one started to get an understanding of what the stars actually were. Now, a big revolution in astronomy came with the work of Copernicus. Copernicus wasn't the first scientist or person to postulate that the Earth was going around the sun. The ancient Greeks believed, or at least the majority of them believed, that the sun moved around the Earth. There were some dissenters, but the general view was that the sun moved around in the Earth. And it wasn't until the time of Copernicus that one had a firm understanding that it was the Earth moving around the sun. But even then, the stars stay the same. If you look at the constellations, it will look the same at the beginning of your life as it will at the end of your life. But it was Edmund Halley who's famous for his discovery or recognition of Halley's comet in 1718, and he observed that one star, this object down in the bottom here, Aldebaran, he compared it with the catalogue that the ancient Greek astronomer Hipparchus made, and he saw that it moved. And about 300 years ago, this was the first indication that the stars are not stationary. The stars are actually moving. At least 3 stars, Aldebaran, Sirius, and Arcturus, observed by Edmund Halley. And if we look at a well-known constellation, I hope I have the spelling correct here. Thank you, Wikipedia. And here is the constellation of Ursa Major, and it's a well-known constellation. And as I said, it will look the same to you on the day that you were born up to the day you would die, and it will look the same today as it did to the ancient Chinese or the ancient Greeks 2,000 or 3,000 years ago. But these stars are all moving. So I'll jump to the where we understand today, and when you look at the constellation, they're not all moving in the same direction through space. You can see that the central 4 stars are moving roughly bottom right to top left, and the outer 2 are moving roughly from top left to bottom right. And we now know, for example, the distance to these stars, and they're not at all at the same distances. I just put the names as they're currently known, and the distance is in light years. Right? I think most of you have heard of a light year, and a light year is the distance that it takes light to travel in 1 year. So you'll see again that these stars are not at all at the same distance. So this constellation, it looks dramatic to the human eye, but it's not a relationship of stars themselves. And we only know that by measuring the distances and motion. Now, Professor Parker has already stolen part of my presentation, because I would like just to Thank you. I'll have the one that wanders round because I wander round. And I would like you, Professor Parker touched on this important point, but I would like you all to be very clear because it's central to my story. Hold your finger up. Have something obvious in the background. It doesn't matter what it is. You can look at a light on the ceiling or someone distant in the audience, and close your eyes, your left eye and then your right eye. And if you look at your finger and look at the background, do you see that your finger appears to have moved? Anyone not convinced? Because if you're not convinced now, you're going to miss the rest of my story, all right? Your finger hasn't moved. And the background hasn't moved. But what has moved is your position with which you are observing that system. And this is an effect called parallax. And it's critical, central to the measurement of the distance to the stars. Now, I'm going to come on later and try and explain to you why it's important to know the distance to the stars, or what this tells us about the universe, or what the space motions tell us about the universe. But let me first lay the basic foundations of this. Just as if we view our finger with respect to the background and we close our eyes, as the Earth goes around the sun, which is what we know from the time of Copernicus, then a nearby star will appear to move with respect to a background star. All right? The effect is very simple. It's trivial. All we have to do is measure this angle, and then we know the distance to the star because we know the radius of the Earth's orbit around the sun. Now, when Copernicus came up with his idea that the Earth moved around the sun rather than the sun moving around the Earth, astronomers realized that if this was true, then this effect of parallax would be measurable. And this would give, for the first time, the understanding of how far it is to the nearest stars, or the scale of the universe. And at that point, starting with the time of Copernicus, people had no idea how distant the stars were, how big the universe was, and so on and so on. So it was a journey of discovery, and it took 250 years between the first searches for this measurement of parallax and the first determination of parallax. And we can try and understand this in the following way. I think it's very difficult to have any visualization at all of the immensity of space. Space is huge, space is absurdly, ridiculously large, and people have tried throughout the ages to come up with some kind of an analogy, and this is actually my own. I think I didn't see it anywhere else. Herschel had the idea that if you had 600 ships, I think it was 600 ships, each of them carrying 500 tons of peas, and if you drop 1 pea every mile, this would take you to the nearest star. I think it's very difficult to visualize 500 ships carrying 600 tons of peas and so on. Here's another analogy. The world's population of 7 billion people, this is a number again which we have great difficulty visualizing, but if we spaced each pair of people by 5,000 kilometers, that would take you to the nearest star. So space is really very big. And the first star distances, after a period of about 250 years, the first star distances, as over this 250 years, measurement accuracies improved. It still wasn't good enough, and then eventually in about the 1830s, the first astronomers measured the first star distances. And the president of the Royal Astronomical Society at the time, John Herschel, I think it was, said this was the greatest and most glorious triumph which practical astronomy has ever witnessed. Now, I'm going to spend a couple of minutes trying to explain this diagram, which shows you how accuracies have changed over time. So I've tried to explain that we need to measure these angles, and I've indicated that stars are at very large distances, so you need to measure very small angles. So let's have a look on this diagram and see what these angles are. And on the axis here, well, this is the easiest one. This is time. Here we are at the present day and going back in time over the last few hundred years, and then a jump to 200 BC or thereabouts. And here on a logarithmic axis, so a factor of 10 jump in each of these scales, you can see the angle that we're measuring in seconds of arc. So this is central to the measurement of parallax and distances and motions of stars. What is a second of arc? You know that there are 360 degrees in a circle. There are 60 arc minutes in 1 degree. There are 60 arc seconds in 1 arc minute. There are 1,000 milli-arc seconds in 1 arc second. There are 1,000 micro-arc seconds in 1 milli-arc second. So we go down to smaller and smaller angles. These, again, are extremely difficult to visualize, but let me try and give some indicators here. The original measurements by the Greek astronomer Hipparchus corresponded to the angular size of the full moon. As we come down, 30 arc seconds is about the resolution capability of the human eye. The Earth's atmosphere, which is this phase-perturbing screen which makes the stars twinkle, imposes an accuracy of about 1 second of arc. And before we had space measurements, this was roughly the limit of practical observations from the surface of the Earth. So astrometry, this branch of measuring star positions, was limited really by the Earth's atmosphere to about 1 second of arc. And what we see on this logarithmic scale, extending over history, is a progressive improvement. And you can see it's a straight line, more or less, with time on this logarithmic scale. But it hit this barrier in about the 1970s, 1980s of the Earth's atmosphere. What has happened since then, through the results of these 2 space missions that I've been involved in, is that the accuracy has taken a very, very sharp increase, further increase in this, even in this linear log scale. It's done this enormous jump. Hipparchus measured just over 100,000 stars with a precision of about a milli-arc second, which corresponds to the angular size of a person standing on the moon, if you can visualize that, or a golf ball viewed from the opposite side of the Atlantic Ocean, from one side to the other. And Gaia, this satellite which is now operating and measuring star positions and distances with extreme accuracy, is measuring these angular accuracies with a precision of about 10 micro-arc seconds. Now again, if one says 10 micro-arc seconds, it means very little. To some of the physicists amongst you, I can say that this corresponds to the measurement of the Bohr radius of atomic hydrogen, so the classic electron radius of hydrogen, viewed from a distance of 1 meter. So you may begin to understand that getting into space is not the whole answer to this. You have to create instrumentation which is extremely accurate, extremely well controlled, and you have to take account of many, many effects, which I will not say really anything more about. But great opportunities by going into space, but is, with all space missions, very, very great challenges. Now, just very quickly, what has happened since these observations have been improving is that we've had a better and better insight into what is going on in the stars, in our galaxy, and so on. So from Copernicus's heliocentric idea became Kepler's laws of planetary motion, Newton's theories of gravity, Halley in 1718 figuring out that the stars are moving, a very important effect discovered by Bradley in 1725 called stellar aberration, which is as the Earth goes around the sun, then the stars appear to move because of the velocity of the observer going around the sun. Bessel in 1838 started coming up with the first star distances, and the big catalogues that were built before the move to space started being used for understanding stellar evolution. Why are stars different from each other? You can determine how stars differ from each other once you have the distance to the stars. You can convert the apparent properties of the stars and you can convert them into absolute properties. So if I know the distance to that light bulb, I can infer the luminosity, the absolute power of that light bulb, knowing the apparent measured brightness from where I am. Hipparchus started making the first, started pushing these distances out to, let's say, a few hundred parsecs. I'll come back to what that is in a moment. And Gaia is pushing this to currently 2 billion. By the end of the mission, it will be about 3 billion objects. And the immense breakthrough that Gaia is offering, this second satellite from the European Space Agency, is actually probing the real structure of our galaxy. So let's have a look at that. This is the Gaia satellite itself just before launch. Everyone has seen the wonderful animations of the James Webb Space Telescope opening its solar panels. Well, Gaia had a similar solar array, 10 meters in diameter. It didn't have the colossal outreach and public relations efforts that NASA did, but here's some of the engineers involved in this. This was folded up against the satellite during launch and then deployed in orbit. This is the heart of the Gaia telescope. It's about a 3-meter diameter silicon carbide torus, so a structure, an optical bench built of silicon carbide. The mirror themselves are silicon carbide. So this is a 1.5 meter times 0.5 meter diameter mirror. Again, one of the most accurately polished mirrors in astronomy, bolted onto this silicon carbide structure. And the great merit, the great power of silicon carbide is that it has a very low coefficient of thermal expansion. It can take a very high polish, and you have no disparity between the thermal conductance or thermal properties of the mirror and the thermal properties of the torus. So there it is. I'm not going to explain how Gaia works in detail. You would need a much longer talk for that. But let's have a look now at what we understand our galaxy looks like. And viewed from a distance, our galaxy would look something like this. We know that. This is the Andromeda Galaxy M31, and our own galaxy, if you could look from the outside, would look something like that. The sun is sitting out in one of the spiral arms, about 30,000 light years from the center of the galaxy. The first satellite that I worked on, Hipparchus, which was launched in 1989, and if you can see this little yellow circle here, this is the radius out to which Hipparchus had a strong influence in determining distances and motions. And with Gaia, we've extended this to distances which extend all the way across the galaxy. Now, for a couple of fun animations, you've understood from the beginning that a star, we're determining the distance to the star through this effect of parallax. So we can reconstruct this. This is an animation, a reconstruction, in which the effects have been exaggerated, but they correspond to exactly the measurements that we made with Hipparchus. And what we'll look at now, this is a region of the sky about 6 degrees. Some of you may recognize, well, it's the Hyades cluster. This would be the size of the full moon on that scale. And as the Earth goes around the sun, you can see here that the nearby stars are shifting backwards and forwards compared to the background stars. This is a 1 year. This oscillation motion is 1 year. So as the Earth moves around the sun in a period of 1 year, this is the kind of effect that we're looking for. Now, let's have a look at something else. The stars are also moving through space. So let me forget the effects of parallax and just put in the effects of the star motion through space. And after careful measurement, this is what we find. This is how the stars are actually moving. Again, highly exaggerated. Over 1 year, over 50 years, you will see nothing. But if you were to apply your cosmic magnifying glass, this is the kind of motion that you would see. And if we add those two effects together, then you can see there that the stars are both moving through space and appearing to move as the Earth goes around the sun. So if you could look at the whole sky under this big magnifying glass. This is the kind of thing you would see happening with every star. They would have their own motion through space, and they would have their own parallax due to the distance to the stars.
À tous de DDO, attention pour le décompte
Well, you've seen a
final.
more impressive, some of you who saw the
10,
previous,
9,
but this is the
8,
launch of
7,
Gaia.
6,
And
5,
I will tell you,
4,
after working for 17 years on a project,
2,
to sit there and
1,
wait for the launch
top, décollage.
and watch this thing and hoping that it will go correct is a very special moment. So remember that rocket, which is vibrating with enormous power, on, carrying one of the most delicate pieces of instrumentation built for space. These are some of the results on Gaia. Again, highly exaggerated, but it's the region of Ursa Major. And unfortunately, I think none of these animations now will have a great impact on you because you've all seen Star Trek and you've seen animations in a way which are very similar to this and even more impressive than this. But this is the kind of thing that we're measuring. And we can also, again, if you could dim, maybe could you just dim the lights a little bit more? Yeah, just for the next couple of slides. Again, this may not seem terribly impressive to you because you've all seen Star Trek, but this is the real distances to the stars, and this is the real motions of the stars through space. Now, I'm just going to talk, the final part of my talk, I'll just talk very briefly about one or two of the kind of science results that which we're examining with Gaia. Again, I'm going to keep this quite short. There are something like 7,000 refereed scientific papers that have been written already on the Gaia results, so forgive me if I only mention one or two. For anyone entering or thinking to continue with studies of astronomy or whatever, like many areas of science, I think we're living in a wonderful time. You are living in a wonderful period. When I started my own PhD, my own research career more than 40 years ago, I think we thought of the solar system as a relatively simple place. It consists of the sun, the planets, the moons, and millions, billions of pieces of rock that we call asteroids and icy bodies that we call comets. And in the last 20 years, with vast numbers of observations of all sorts of different things, we've understood an enormous amount more about the solar system. But that search continues, and the solar system seems to be a more and more complex place with more and more complex phenomena going round. And what I'm going to show here is just some of the first results coming out of Gaia on solar system objects. So we're not only measuring stars, but we're able to measure asteroids, because down to the limit of observability of Gaia, we're observing at the moment something like 200,000 asteroids, and there will be more in the final catalogue. And from the many observations that we piece together, you can determine the orbits of these objects. And in this little animation, we're looking down at the solar system. Here's the sun, here's the Earth, here's Jupiter. These are the Jupiter Trojans, asteroids that are moving in a kind of gravitational well of Jupiter. These are focusing on the near-Earth asteroids, and now we'll do a little fly through of the near-Earth asteroids near to the Earth, and continuing a video, of course, highly speeded up, but again, with the real motions of these asteroids. This is not a simulation. This is not the product of something. This is the real distribution of asteroids and how they move. And the different colors there, all these asteroids are basically lumps of rock, but they have very different chemical compositions. And as sunlight is reflected off them, you see essentially a different color or different spectra, and Gaia is recording these as well. And hidden in here is an immense wealth of information about how the solar system came into being, how it originated, and so on. As one example, perhaps many of you recall something like 5 or 6 years ago, the discovery of an object flying through the solar system. We can tell from the motion of this object that it didn't originate in the solar system. It must have come from another solar system, another stellar system. For those people who study the formation of planetary systems and the studies of extrasolar planets, it's not really surprising that from time to time there should be a piece of junk from one of these other solar systems passing through our solar system. We can recognize that from the orbit. And what Gaia is able to do now, because we know the motion of our own sun through the galaxy, and we know the motion of all the other stars near to us, we can propagate the orbit of this object backwards in time and try and say which of the nearby stellar systems this particular piece of rock came from. For those of you, I'm just going to put one view graph in here, because for those of you who know a little bit about astronomy, there's something very famous called the Hertzsprung-Russell diagram. And in this diagram, you plot the luminosity, the absolute luminosity of the star, which you can only determine if you know the star's distance. And here you plot the color or effective temperature. And what happens is that all the stars around us, the hundreds of thousands or billions of stars around us, sort of line up in this remarkable diagram, which is telling you a great deal about the formation and evolution of individual stars. Our sun sits somewhere here, and it will sit here for the next 4.5 billion years, burning its hydrogen fuel. The giant branch is where stars end up as exhaust their hydrogen fuel, and down here you've got the white dwarfs, the end state of stellar evolution for most stars, most low mass stars. And just one of the many insights that we're getting from Gaia, I'll circle that region here, and if you can see this little excess of stars, a tiny excess of stars here, the people working on this, of course, first think that you've got an error in your data, but soon realize that this is an effect that was predicted 60 years ago independently by an American astronomer and 2 Soviet astronomers, and it's indicating that the white dwarf is actually crystallizing. The center of this white dwarf is turning from a gaseous plasma into a solid crystalline core. The core is moving outwards at about 1 centimeter per second. Our sun will become a white dwarf in about 5 billion years, and it will start crystallizing from its center another 5 billion years beyond that. Now, if you're asking yourself, well, how on earth can we say that this little line of stars here is due to white dwarf crystallization? Please do your PhD in astronomy and start answering these questions for yourself. But I can tell you that there are thousands of these sorts of questions now opening up. It's a wonderfully rich field. I just show quickly gravitational lensing. Gaia is detecting many of these. These stars are themselves not flashing like a lighthouse, but what is happening is other stars are moving in front of these stars because of their motion through space, and space-time being curved according to Einstein's theory of relativity. The light from the background star is actually focused and bursts like that. I'm close to the end. I've run out of time, have I? A very important point is that we're now understanding much more about the origin and evolution of our universe. We seem to have a good working hypothesis, the Big Bang, cold, dark matter. And according to this model, we feed in, the people working on these simulations feed in descriptions, very simple description of what we understand about the universe. And then you see structure arising over billions of years. And guess what? It looks like our own galaxy and perhaps the Large Magellanic Cloud. So observations today are very much guided by these theoretical models, which are showing how structure is formed in the galaxy. And what we see in our own galaxy is these loops, these trails of stars. This is a little cartoon of our own galaxy, and out in the halo of our galaxy, we see trails of stars. they have the same motion, they have the same elemental composition, and they trace ancient galaxies, small galaxies, which have been cannibalized by our own galaxy over the past few billion years. So that brings me to the end. What's a little bit of a takeaway? This is where we are. Gaia is measuring distances of motions of more than 2 billion stars. Everything is moving. We're getting a three-dimensional picture of that. The Gaia satellite was launched in 2013. It's still operating today. Improved catalogues will continue to come out for the next 7 years or thereabouts. It's making many new discoveries about the formation and evolution of our own galaxy. And several thousand scientific papers have already been published touching on many areas of astronomy. I'm standing up. My co-awardee of the Shaw Prize, Lennart Lindegren, was another one of the great leaders of astrometry. Beyond that, it's an enormous collaboration of scientists, of brilliant scientists, brilliant people contributing in all sorts of areas. Let me stress the role of industry, because they don't get, I think, all the recognition they need. It's all very good scientists dreaming about some wonderful measurements that they want to make, but it is our engineering teams that convert these into reality. Funding and management, European Space Agency. Something like 30 European institutes were involved in the construction of Gaia. It furthers industrial techniques, knowledge, expertise, capabilities. It's operated by ESA's Operations Center in Darmstadt, and today about 400 scientists and astronomers are actually involved in processing the data, not just interpreting the data, but processing it. So I have, in my retirement, sitting down, I have my own little website. I've got, I write a weekly essay on different Gaia results. I've got some animations collected there. I've got some interviews with some of the leading scientists and industrialists and policymakers involved in that. And that only leaves me to say, thank you very much for your attention and for your invitation.
Thank you very much. Thank you very much, Michael, for a real tour de force there in going through the achievements and scientific capacity and capabilities of the wonderful Gaia mission. So let's thank our speaker once again. Absolutely fantastic. So now we've got about a question and answer sequence that will last for 7 minutes. So could first see if there's any questions from the audience. Yes, we have a question here.
The badge got stuck. Thank you so much for the wonderful talk. I'm Rafaela So. I'm a biochemist at the University of Toronto. And so my question is more related to the earlier parts of the talk about the parallax approach to measuring star distances. I was wondering if you said that you use the farther stars as like an anchor to measure the nearer stars. Then how did you know how far the farther stars are to start with? Like, where did you start?
You should move out of biology, because of course that is a very, very critical question. It's a very fundamental question, and it's one of the reasons why ground-based astronomy has struggled, because you don't know how far away the background stars are. Now, the answer to your question is quite complicated, but I give a simple answer, and that is that we can tie all these observations to the observations of quasars. And quasars are objects which we know, we believe, are very, very distant, and therefore their distances are essentially zero. We observe something like 10 million quasars with Gaia. So the stars are directly tied into a reference system of these objects that we know are at very, very large distances, essentially with a zero parallax. The answer is a little bit more complicated than that. It's a great question, but I'll leave my answer there.
Yeah. Thank you. Quasars are the sort of extremely energetic hearts of galaxies themselves, so that's why they're so far away. Okay, another question from the audience? Yes, we have a very young person asking a question at the back.
How long is the universe?
You know, when you work in science, you are very conscious that you actually don't know very much. And I work in this area of measuring these star distances. There's other people, there's cosmologists who talk about how big the universe is. And I think it's a really complicated question with a really complicated answer. As far as we know, the universe extends to enormous sizes that we can't see the edge of. And the answer is really that we don't know how big the universe is, and we don't know how the universe came into being, and we don't know what happened before the Big Bang, and we don't know why matter appeared apparently out of nowhere. All of these questions we don't know, and maybe you will be one of the people that helps answer that.
Okay, I have a question that's come in from the remote attendees of this special lecture. So the first question is, how does white dwarfs evolve in the HR diagram in the process of crystallization? Are they getting bluer from the main white dwarf trail?
So what happens, essentially what you see there is white dwarfs cool. They finish their nuclear burning, they have no more nuclear fuel, they have no more hydrogen, helium, or anything else that's burning. So they just sit there and cool. They radiate their energy into deep space. And we can calculate roughly how long they will last, how long they will continue cooling, how long they will continue to be there, radiating their energy away. And in general, it's many, many, many times, 10 times, 100 times, 1,000 times the current age of the universe. So they just continue radiating their heat for a very, very long time. As they age, they get progressively cooler. So they do move slightly down and slightly to the right. And that's a very gradual and slow process.
Thank you. I've got a few questions that came in earlier, and I'd like to maybe just ask one of them before we get back to the audience. And that is, in your eyes, what were the most significant and astonishing discovery from Gaia?
I think it is this area that I touched on at the very end, that we now start having a picture of how our galaxy really formed. I think until Gaia came along, we thought that the stars are sort of roughly moving in circular motion in this spiral pattern. And what we see now in Gaia is a rich variety of phenomena, of motions, of star motions, of resonances, of effects due to the spiral arms and the bars and so on. We see these satellite galaxies that have fallen into our own galaxy and been captured by our galaxy 10 billion years ago, early on in our own galaxy's formation. So I think we're starting to have a first very, very clear picture of how our own galaxy came into existence. And we are confirming many of the models of the existence of dark matter and the halo of our galaxy and so on. But it's understanding how our galaxy formed.
We have time for just one more quick question. There's a young man with his hand up, vigorously shaking it around, so let's give him a chance.
Just a slight question, but after white dwarfs crystallize, do they enter another stage, or do they keep radiating heat until they lose all of their energy?
Who was this that put you up to the... This isn't your question, is it? Is it really your question? It doesn't matter. Right. So there's lots of papers being written on this now. That white dwarfs are a really exciting area of research. And what happens in the crystallization, you know perhaps that if you have an ice cube, right, you measure the temperature of that, you start heating it up, and it sits there at 0 degrees centigrade all the time that you're heating it. You're putting more and more heat in, but it stays at the same temperature while it changes its phase from a solid to a liquid. And the same thing happens the other way around. When you cool something from a gas and it crystallizes into a liquid or a solid, it holds up that cooling process. So that's why we see this little gap in the line there. But people are starting to look at many other of the physical aspects of the cooling process. And it does seem as if there's a whole new area of physics in there where you can start seeing an effect called Debye cooling, for example, in these. But there's lots of scientific research papers now being written on that. So thank you for the question again.
Thank you. Well, we've run out of time, so let's just thank all the people that asked questions. Please just thank everybody for all the fantastic questions. And of course, let's thank our wonderful speaker again, Professor Perryman.
Thank you.
What a great pleasure. Thank you very much. Thank you. Okay, so now we get to the second part of this dual heading presentation, and it's now giving me great pleasure to introduce Professor Ming-Chung Chu from the Chinese University of Hong Kong. He's a very eminent astrophysicist in his own right, and also a particle physicist. He's done tremendous work at Daya Bay in neutrons, and he's had a very illustrious career. And so he's going to be giving us a presentation today on Twinkle, Twinkle, Little Star, which I think some of us may have heard of before, but he's going to tell us a lot more about it. So without further ado, Professor Chu, please come to the stage.
Thank you. Thank you very much. I'm really honored and really happy to be here. Particularly happy to see all these young kids. I fell in love. I myself fell in love with astronomy when I was a secondary school student in Hong Kong. First time I looked at the night sky, seeing all these stars, I decided that I have to do physics, astrophysics. So I'm very happy to see you all here. So the title of my talk is Twinkle, Twinkle, Little Stars. I wonder what you are. And I'm serious about this title, particularly about the little stars. It's always amazing to think about how many stars there are. Just Milky Way alone, we're talking about 100 billions of stars shining on us every moment. And about 10% of those, roughly speaking, are white dwarfs. And we already heard a lot about white dwarfs. About 1% are so-called neutron stars. White dwarfs and neutron stars are the little stars that I'm talking about. So these are little stars, but it's actually not so difficult to see some of them. Okay? So here you can see a white dwarf. And they're often associated with nebulae, very beautiful objects in the sky. So these are stars that just sort of died. Okay? Neutron stars, okay? This is the famous Crab Nebula. And again, if you sort of zoom in, you can see a little star hidden inside. Now, these are amazing objects. If I compare the sizes, this is our sun. Earth is about this size. A typical white dwarf is about as large as the Earth. Okay? You squeeze about one solar mass into 6,000 kilometers in radius, then you got a white dwarf, typical white dwarf. A neutron star is only about 10 kilometers in radius, really tiny. But they're very massive. They're about as massive as the sun. So you can imagine that these are really very strange objects in the universe, and they're all around us. So white dwarfs are believed to be supported by so-called electron degeneracy pressure, which basically just means that there's a Pauli exclusion principle. Electrons cannot take up the same energy states, and therefore it takes a lot of energy to squeeze them together. So you feel some resistance which supports the star from its own gravity. Now, if you take the radius of these white dwarfs and plot it against their masses, so each dot here represents one measured white dwarf. The standard theory would predict this radius-mass relation to fall in this band between the orange line and the blue line. But now we got more and more data, and there seems to be many white dwarfs that deviate from this standard theory. Now, in particular, there are many white dwarfs that are way too small. Also, some that are very large. There are even white dwarfs that are supermassive. So, they are really interesting. Just 2 years ago, there is this paper in Nature discovering a white dwarf which is moon-sized, even smaller than Earth. Really a little star. Now, how about neutron stars? Okay, so this is Hong Kong, a small city. If I put a white dwarf, it will only cover Kowloon and Hong Kong Island. Okay, I always try to keep it away from CUHK. Okay. Yeah, so, oh, sorry. Can you put it back? Yeah, if you put a neutron star in Hong Kong, this is what will happen. Okay? Great, thanks. So a typical neutron star has radius about 10 kilometers only, right? That means there's a huge surface gravity. A typical human being would weigh 5 billion tons. So immediately it will collapse. That's why these stars are extremely spherical. There will be no hues at all. Nothing can stick up from its surface. So you can think of a neutron star as a giant atomic nucleus. All the neutrons, protons, a little bit of protons packed closely together. A teaspoonful of neutron star material should weigh 6 billion tons. Okay? So this is a very interesting playground for physicists. And in fact, the physics of high density matter is still pretty much unknown. Lots of uncertainties. We don't really know what's inside a neutron star. Okay, now recently, if you pay attention to the news, about a few months ago, there's a lot of news about pulsars. Okay? Pulsars are neutron stars. They have such a high magnetic field that they will beam out high energy particles. And if these beams sweep past us, then we'll get some signals. Okay? So we'll get very regular signals from pulsars, and the periods of the signals would be the rotation period of these pulsars. So I made a quintet out of these 5 pulsars. Okay, this is the world premiere of this quintet. So let me play it for you. Okay, this is what you would hear if I convert the signal into sound. This is 1 pulsar, 2 pulsars, 3 pulsars, 4 pulsars. Now we have a full quintet. It's beautiful music, right? Okay, so a few months ago, scientists all over the world made use of these pulsar signals to measure something we call gravitational waves. And they believe that the signal they picked up correspond to gravitational waves generated by two merging supermassive black holes. This is really quite an achievement and caused a lot of excitement all over the world. So neutron stars are not only interesting by themselves, they turn out to be very useful to help us to probe other objects in the universe. Now, white dwarfs and neutron stars are extremely important in stellar evolution. They are believed to be the end stages of stars. So there's, in any astronomy textbook, there's a standard theory about how stars evolve. Okay? Depending on the mass of the star, they will evolve into white dwarfs, neutron stars, or black holes. These are the end stages. And white dwarfs could also blow up as supernova. And these supernovae, some of them, might produce the neutron stars. And supernova, being such powerful explosions in the universe, they're also extremely interesting. Okay, next I will just briefly tell you a little bit about our interest in these little stars, white dwarfs and neutron stars. Okay. Quentin already mentioned that I'm also a particle physicist, so I've been interested in measuring elementary particles. So for example, we joined a large experiment at the Large Hadron Collider using a huge particle detector called ATLAS to measure elementary particles, such as the Higgs boson. Okay? So it's a huge detector. If I put it right next door, it would be even larger than our favorite planetarium, the Ball About. Okay? Huge particle detector, right? Now, an even bigger particle detector is this one called IceCube. Scientists are very clever. They made use of the ice in the South Pole and just put some instrumentations down the ice to set up a huge particle detector. Okay? They've made a lot of new discoveries. Very exciting discoveries. So I started wondering, now we don't have funding in Hong Kong to build these kind of particle detectors. No way. I don't think I can convince Li Ka-chiu to give us money. Okay? But we have so many white dwarfs and neutron stars. So is it possible that we make use of them as particle detectors? Okay. So these will be even larger particle detectors than IceCube or ATLAS, much, much larger. And there are billions of them, even within Milky Way, and they all come for free. Okay. That's the best part, right? So many astronomers make wonderful observations of these stars, and astronomers are really nice. They just upload the data, so everybody can look, can analyze them, can study them, all come for free, all open. Okay? So we ask ourselves, now if white dwarfs and neutron stars, if their properties depend critically on properties of particles, then maybe we can turn them around and make use of them as particle detectors. Okay? Particularly when white dwarfs die and giving rise to neutron stars. Okay, so we like to play with the idea that how can we make use of them as particle detectors, right? So roughly speaking, we have been working on using white dwarfs and neutron stars as dark matter detectors, as well as to search for a new phase of matter called quark matter. Now, I don't have time to really go through a detail, and it would be way too technical for most of you. So I will just very quickly give you a flavor of what we have done. Okay? So about 10 years ago, I asked these two kids, well, they're really university students, okay, but I always think of them as kids. what happened if we put some dark matter into a white dwarf? Okay. So after some calculations, they came back and told me, well, they'll shrink down in radius dramatically. Okay. So this is showing mass versus radius of white dwarf mixed with some dark matter. Okay. So we found that without dark matter, we have the typical white dwarf mass radius relation. If you just add 1% solar mass dark matter into typical white dwarf, it shrinks in radius. If you add 5%, it becomes much smaller. And we already predicted 10 years ago that there could be moon-sized white dwarf if you just add a little bit of dark matter into them. So if some dark matter could get into white dwarf, changing its structure, what would happen when the white dwarf explodes as a supernova? Okay, so we call these type 1a supernova. Could we explain some of the peculiar type 1a supernova? Okay. So I asked another kid, who is now a PhD student in the States, and these two kids performed some hydrodynamic simulations to compare type 1a supernova with and without dark matter mixed. Okay. So these are the simulation which runs so slowly. I don't know why. I guess the animation won't play. Doesn't matter. But in the end, we found that mixing some dark matter in would make the supernova much dimmer, and the light curve would be changed dramatically. We could actually fit the light curve of some of the so-called peculiar supernovae. So it's possible that indeed some of the type 1a supernovae, which deviate from the standard ones, maybe indeed there are some dark matter mixed into them. And by doing these simulations, we also find a way to make pure dark matter stars. So basically a white dwarf, if it's mixed with dark matter, after a supernova explosion, we found that most of the time, the normal matter got expelled, leaving behind dark matter core. So there might be these dark matter compact stars in the universe. I don't know how we can observe them, but it will be very interesting. And they will be yet another kind of little stars. All right, finally, we also ask ourselves, well, we don't know what's inside a neutron star, right? It's so dense. Could it be not just neutrons sitting inside? Could it be that the core of these neutrons, of some of the neutron stars at least, are made of quarks? Quarks are believed to be the elementary particles making up of neutrons and protons. So usually, we only see protons and neutrons, but under high pressure, high density, maybe the quarks sitting inside the neutrons and protons will spill out, forming so-called quark matter. Okay. And this could happen when a star undergoes so-called core collapse supernova. So at the end stage of a massive star, the core would collapse in a fraction of a second to a tiny core, which we call a proto-neutron star. And the density would be so high, and sometimes the temperature also very high, that it might be possible to go through this phase transition to a quark core. So again, we perform, sorry, I should not have clicked it. So could you click it for me? No, it also won't play. No? I cannot, sorry. Doesn't matter. These are animation that we can perform simulation of these core collapse supernova, and we can predict what would happen if there is a formation of a quark core. Okay? So basically, we could calculate the gravitational wave signal. There would be two bursts of gravitational wave signals if there is indeed formation of a quark core. So we're anxiously waiting for the next core collapse supernova in Milky Way. If that happens, if it's close enough, then there'll be many different detections, both in electromagnetic waves, neutrino signals, and gravitational wave signal. We'll know much more about the core of these supernovae and whether there will be quark stars formed in these processes. Okay, so it doesn't matter details. Okay, these are just some of the ideas that we play with because we love these little stars so much. Okay, now my final takeaway is that there is already, and there will be even more, a huge volume of high precision, high quality data about our stars, including these little stars. I think it will be a completely new era. We're going to understand much more about these compact stars. And hopefully, we might even be able to find new physics. And somehow this is not the original PowerPoint I have. Okay, but I will stop here. Thank you very much.
Thank you so much, Professor Chu. Please remain on stage as we're about to move to the upcoming panel discussion. But before that, a big round of applause to our scientists and also to Professor Perryman and to Professor Chu for sharing with us some of the very intriguing and fascinating presentations. I'm sure we've all learned about the latest discoveries and also some of the very groundbreaking quintet that Professor Chu just showed us, and also some of the illustrations to let us learn about how the galaxy, our Milky Way Galaxy, is actually moving in different motions right now. And now, ladies and gentlemen, we will now soon be moving on to the panel discussion, and it's now time for you to raise questions. Just as a kind reminder for our audience in the room right now, you may raise your hand and our staff will pass you a mic to ask the question. And for our online participants, you may submit your questions on the HKLF mobile app through the Q&A function. Now, without further ado, may we please invite Professor Perryman and Professor Parker to join Professor Chu on stage again. Let's welcome our scientists with a big round of applause. Thank you. Please be seated. And now, Professor Parker, over to you.
Oh, thank you very much. Well, I've got a sort of a précis here about what I'm meant to be talking about, but I'd just like to first say thank you very much, both of you, for including at least one image of a planetary nebula in your presentations, because that's what I work on, which is kind of dying stars before you get to a white dwarf. So anyway, there's been a tremendous advance in an incredible number of facilities available, both on the ground and in space, over the last decade or so, with many more planned. China's got its own space station telescope, which is going to go up now, we think, in 2025. It's about a 2-meter UV optical telescope, similar to the Hubble, but with a field of view that's 300 times larger. We've got facilities like Gaia that's still producing incredible data. We've got Euclid that's up there now. We've got, the Fast Radio Telescope in China, the world's largest single-dish radio telescope, and perhaps several other of those will be built. So we've got LIGO. We touched on the gravitational wave astronomy. This is now when we're no longer doing astronomy with photons. We're now doing astronomy with things called gravitational waves, which sort of compress space, compress materials. And we're measuring strains of 10 to the minus 21 of a meter. I didn't think I would see gravitational wave astronomy in my lifetime. I didn't think we'd get the technology, but we have. So with all these incredible facilities, we're entering a new golden age of astronomy, I think. So the first question I have based on that brief introduction is, what are they most excited about in possible new discoveries from all these tremendous new facilities that are coming online? And so therefore, what is the next frontier of space science? I think...
Yes, it is. I think amongst my skill set, predicting the future is not perhaps my greatest, because you know, things move so very, very quickly. And I think I tried to make the point, and Professor Parker has made the same point, that this is a wonderful time for young people to be entering the field because there are so many facilities coming online. There's another one, the Rubin Observatory, which will be making many frequency observations of the sky. And we're continuing to see these new phenomena turning up, fast radio bursts, which we didn't know anything about, and they really seem to be impacting on or unearthing potentially new physics. I think, there's so many questions there you can answer. And I think with all these facilities, I mean, the way science works is that these facilities help you to answer one set of questions that are being posed. But they also open up many new questions as well. I think, I mean, that was a little bit of a background, but I think the gravitational wave domain is a really exciting one. I myself actually chaired a panel for the implementation of LISA 2015-2016, and I have been quite frustrated at the length of time that this mission is taking to implement. I think we have the capability now, we have the industries now, and it's a question that needs answering now. The current launch schedule for LISA, the European NASA gravitational wave antenna in space, has been pushed back again to something like 2037, which I think you can even see from that presentation, your presentation, Professor Xu, that there are ideas there, new ideas about things to search for in gravitational waves which didn't exist 5 years ago. So it's opening up a new field. I think that is a very exciting one. I just hope I live to see the day when gravitational waves are being in space. I think China has also its own independent plans for gravitational wave detector. But really there's so many things I wouldn't know quite where to.
I think we'll have a moon base by then as well, by the way. So anyway, here's another question that's come in. I think this one is for Professor Chu, and that is, what is the number or percentage of white dwarfs and neutron stars in our galaxy?
Right. So I actually only looked it up from Wiki, okay? The estimate is about 10% of all the stars are white dwarfs. So we're talking about billion or so of white dwarfs. And 1% are neutron stars. So we're talking about, 10 billion white dwarfs and 1 billion neutron stars. And of course, these numbers are highly uncertain, okay? Just a rough estimate.
So just a quick follow-up from me on that. Of the billion neutron stars, how many of those are close enough that over Hubble time they're going to coalesce and therefore give us lovely gravitational waves?
In fact, so far we could really only measure accurately the signals from neutron stars within our Milky Way, okay? Now, they could measure some neutron stars from other galaxies, but the quality of data is not there yet. Right?
Thank you. So questions from the audience? Yes, young man. Can we get him a microphone, please?
Thank you, professors, for your sharing. So just now, Professor Chu mentioned about putting a little bit dark matters on the white dwarf. So I wonder, if you put a white dwarf into an infinite dark matters, like a pool of dark matter, infinite, and then will it shrink into a particle size?
Yeah, thank you for the question. Excellent question. So before I answer your question, indeed, we thought about such scenarios, but not in terms of white dwarfs, okay? So we were actually thinking about what happened if the merger of binary black holes happened in a sea of dark matter. Could we make use of binary black hole merger to probe the dark matter that surround them? Okay, and so you can play around with such ideas. Okay, now, however, the standard picture of dark matter is that they are very diffuse. So a very dense white dwarf sitting in very diffuse, very dilute dark matter background probably won't do much. Okay.
Okay, more questions. Yes, we've got one there, young lady there with her hand up. Could you please say whether you're addressing it to Professor Chu or Professor Perryman, please?
I must thank both professors for such an eye-opening speeches. And I have a question for Professor Ju. As we all know that the universe is expanding beyond the speed of light, and the stars are leaving the solar system, and there is a prediction that originally our galaxy will collide with another galaxy that's moving towards us. But now that the universe is expanding at such speed, will this prediction actually come true?
Okay, thank you for the question. Professor Perriman showed you the image of our next door neighbor, the Andromeda Galaxy. Okay, our Milky Way and Andromeda Galaxy are actually moving towards each other. Probably will merge together to form a larger galaxy. Okay, if I don't think I can see it, maybe you can wait. Okay, so yes, the universe is expanding, but for galaxies that are close enough, the mutual gravity is so strong that they would still move towards each other. And in fact, now we know galaxy mergers are quite common. Many galaxies could interact with nearby galaxies, they could merge together. And because they're so close together, the mutual gravity would be strong enough to overcome the overall expansion of the universe.
Would you like to add something to that?
Let me just add one point to that. I mean, you shouldn't be too worried about the collision of the Magellanic Cloud with our own galaxy, because it will happen. I think it's something like 50 million years or thereabouts. But again, the point to bear in mind is space is so huge and space is so empty that when these galaxies collide, they more or less pass through each other. The stars, even then, the stars will not collide. So it's one less thing really to worry about.
Yeah, that's true. Exactly right. You get tidal disruptions, which you can see in like examples like the antenna galaxy, but when they go through a first pass, there's more than one pass. They don't or even merge straight away necessarily. Okay, now here's a question I'd like to put to Professor Perryman that's come in. I have a list here. Is given that you have this website, sir, that has interesting lectures and videos and all sorts of stuff on, how do we popularize astronomy as a fun and interesting subject for our young scientists to pursue?
I don't know.
Okay.
No, I mean, it's a fascinating question, and I don't know. I love to respond to an invitation like this because you hope you get some people, some students or some young people who you can pass on that enthusiasm to.
Yes.
I think making an effort to explain the very difficult subject that we work with is very important. And maybe just one comment on Professor Chu's work there. You see really science in action now. You know, he talked about dark matter. We don't even know dark matter exists, but he's made a prediction, and you can follow that prediction and observe that. And if that is proven to be, if his predictions are proven to be true, he's essentially proven the existence of dark matter. So I think communicating the excitement of science, the fact that there are questions, you know, it's as the expansion of knowledge is sphere, and as you go further out, there's more and more to discover. So it's a very exciting time. That's the message to communicate to young people. And it doesn't matter whether it's astronomy or chemistry or geology or biology or whatever. It's a period of, you know, wonderful opportunity for young people.
I think that's actually right. And, just thinking about talking about dark matter and Gaia, and this thing I was reading recently about modified Newtonian dynamics coming back into play, potentially with almost a 5 sigma result coming out, that shows perhaps you've got to go back again and look at this as an alternative as well to explain some of the signals we've been seeing, not necessarily all due to dark matter. So I think that's very interesting. Okay, further questions from all of a sudden, there's loads of hands going up. Let's pick one. A guy waving his hand vigorously first at the back in the red and grey.
A question for Professor Chu. You mean, when you say quark stars, you mean the quarks are not confined. So beyond neutron, protons, pentaquark, tetraquark.
Right, right. The quarks are all deconfined, and it's not new, okay? People doing collider physics, they could collide heavy ions, high enough energy, they believe that for very brief moments, quarks and gluons are deconfined, okay? So the existence of that phase is not new. Whether you could find such a phase with deconfined quarks inside the core of a neutron star, that is the question.
So how can you ascertain that a star is a quark star? Or even further, how would you recognize that a supernova is a quark supernova?
Right, right. That's exactly why we need to do these simulations and modeling, okay? So you can always put in your computer, we're like God, okay? You can change the physics, we can compare a supernova with no quark star formation with a supernova that has a quark core, and we compare the different signatures, observational signatures, okay? So I went too fast in my talk, but if there is a further collapse in the quark star, there'll be two bursts separated by a fraction of a second, two bursts of neutrinos, two bursts of gravitational waves. So that's very distinct signatures.
Okay. And they would arrive at the same time?
No.
No.
The two signals will be separated by a fraction of seconds.
Which one is faster?
The first one is a normal collapse. Okay. The second one is a collapse of quark stars. Okay.
Right.
However, even you observe that, you still don't know whether you have a quark phase or something else. Okay. So it's ongoing research. If indeed this is observed, that would be very exciting, and then many scientists will rush in to try to come up with alternative models, and maybe, hopefully, one day we can come up with a very unique smoking gun signature of a quark star.
Thank you.
Okay, we've got about just over 5 minutes left, so it's enough time for 2 or 3 questions. So a question for Professor Perryman, please. Yep, okay, thank you.
Thank you. I guess this is really a question for anyone, but as someone who works in maths, I often get asked what I add to society. I think that's a bit easier to answer in some sciences than others. Maybe astronomy seems to me a bit more difficult. So, I mean, how would you respond to a question like that? What does an astronomer add to society?
I would add to that in 2 parts. The first is, of course, cultural. For those people who work in biomedics or medicine or whatever, extending the lives of people and so on, you know, I could be quite provocative, say, what is it spending their lives for? It is to enjoy perhaps company of other people, music, art, and scientific understanding. It's part of our culture. That's the it also provides this sort of avenue for humanity is intrinsically curious, and by pursuing this, you're satiating curiosity. But let me make another important something like the Gaia satellite cost that $500 million doesn't go up in smoke. That $500 million goes into developing industrial capabilities, pioneering forefront, cutting-edge technical capabilities, which is then used by these industries in other applications. So space technology in fundamental space area is an example of where basic science, fundamental science, is contributing to economic growth. And that is at the core of a number of different economic models. Invest in pure science, invest in fundamental science, and you grow your economy by facilitating and improving not only the industry, but also people working together. This is human capital, which is also very, very important in societal growth.
Indeed, there are many examples of astronomy that's delivered things that completely out of left field that you didn't expect, serendipitous almost, like Wi-Fi. That came from CSIRO Radio Physics in Australia. Good on you. Okay. Okay, time for another question or 2. Yes, young lady.
Thank you for your question. Thank you for your talks. It was very awe-inspiring. So as a young scientist like myself, and along with a lot of people here seated in the audience. So do you have? Because sometimes in research, we always get really frustrated because you don't get any results. We get results years later. So do you have anything to say about this, or to encourage people to keep pursuing despite all the difficulties? Thank you.
If you want to hear about the obstacles that I have encountered during my time with these space missions, I think we'd need a much longer session. You could also ask my wife, who probably has a very detailed chronicle of them. But yes, in whatever field you decide to move into, whether it's scientific research or business or teaching or education or whatever, you will meet obstacles. And, I think it just comes down, you will meet these obstacles. They're not aimed directly at you. They occur because you're working with other people, you're working with systems that you can't control. You will have setbacks in your research. That is part of them. And you've got to have the sort of desire to overcome those. I think that what probably marks out partly a great scientist from a good scientist or a non-researcher or whatever. It's this ability to continue to pursue. It's not only having the insight, the curiosity and so on, but having the tenacity to face these obstacles and overcome these obstacles. I don't want to go into the sorts of obstacles I've had. I've had many. But you've got to have the tenacity to overcome them and seek a way through to your final goal.
Okay, we have thank you very much. Time for one more question. And how about from somebody over this side of the auditorium? We haven't had a single question from you guys and girls. So come on. Question from over here. One question. Hand up, somebody. Oh, okay. Nobody. Right, okay, well, back over here. Yes, young man in the middle. Yes. That's the last question.
Hello, I'm Chen Liang from Shanghai Astronomical Observatory. I have a question to Professor Zhu. So in your work about the dark matter, so what's the mechanism, so what type of dark matter are you considering? And what's the mechanism to radiate away the kinetic energy to squeeze enough dark matter into the tiny white dwarf? Thank you.
Right. Thank you for the question. Yeah. So for the results I've shown you, we worked with fermionic dark matter. So that, and we assume that they're degenerate, so that there will be also degeneracy pressure there. We do not assume this dark matter being captured after the white dwarf is formed. We assume that they're formed together with the white dwarf. Okay. But we can discuss all these technical issues later. We are currently also working with bosonic dark matter, so we should try all sorts of dark matter models. Okay.
Okay. Well, you finished exactly 2 seconds after the end of time. Perfect. So, first of all, I've been very impressed with the sophistication of many of these questions. I don't know about you, I was pretty impressed. So let's thank our two wonderful speakers again. Now, hand back to the MC.
Yes, thank you very much. Thank you so much, Professor Chu, Professor Perryman, and also Professor Parker. Thank you so much for hosting this insightful discussions. And also, thank you so much for your participation. Once again, a big round of applause to our scientists. Thank you so much. Please take your seats with our audience. Please be seated with our audience as we'd like to commemorate this very special occasion with a couple of photos. Please be seated with our audience. And may we invite our photographer to come on stage so that we can take a photo with everybody, including our show laureates, our scientists, and also our audience. And do we need to move our audience from the left to the middle? Would you like to do that? Okay, it's okay. And now onto the camera first. And we also have some props to hold. The Hong Kong Laureate Forum. Okay, let's get ready and smile at the camera. And now, please wave to the video. Thank you. And now, ladies and gentlemen, as time flies, we've now come to the end of this program. And this is also the finale of the inaugural Hong Kong Laureate Forum. Once again, we'd like to show our gratitude to our speakers for their knowledge imparted over the past week. Let's give our speakers a big round of applause. Thank you so much for your time and dedication. And last but not least, we'd also like to thank everybody for being with us the past week. Thank you so much for your time and participation. And we look forward to seeing you once again at the Hong Kong Laureate Forum events in the future. Thank you so much. Take care and goodbye.